Thank you, Noah. Why you might want to go async. Hi, I'm Jonas. I am originally from Switzerland in Europe. However, the last 5 years or so, I have lived in Tokyo, Japan, where I work for HD together with Iskander, who's also here. And hi, I'm Jonas. I work for HD, and very quickly, I just want to introduce you to the HD internship program because I think it's quite unique and really, really awesome program. It's an internship program where we will fly you to Japan and back and make sure you have a place to stay and you have food and you're doing well. And we will teach you what it means to be working in a Japanese company, or rather in our Japanese company. And the internship program is, strictly speaking, not paid, but it's kind of paid. There's some legal reasons why we cannot tell it's paid, but whatever. And it's open to students. You don't have to have graduated yet if you're still doing your studies. And if you're interested, please come talk to us or check out our website. Some quick links. If you have some complaints about my talk today, you can reach me on Twitter. If you want to look at some code I wrote, my GitHub is github.com/ojii. And our company's website is hd.co.jp, where you can find out about working for us. So let's get started with my talk, why you might want to go async. As I wrote this talk, I realized that this talk title is actually really, really, really bad. Because before I can talk to you about why you might want to go async, I probably should explain what I mean when I say async. So, async. Async is short for asynchronous. But when I talk about async, what I mean in particular is asynchronous I/O, or even more in detail, asynchronous network I/O. Meaning every time you try to access a server, or you are on the server and you wait for the client to send you data, if you're doing a database query and you wait for the response, that's network I/O. And that's what we are talking about here. And simply speaking, it's the opposite of synchronous. So let me give you some examples about what synchronous libraries are in Python. Probably the most famous ones these days is requests, which is a synchronous client library to do HTTP requests. There's Django, there's Flasks if you want to do websites. If you want to talk to Postgres, you use PsychoPG2. If you want to talk to AWS services, you use Podo3. And generally speaking, most libraries out there these days, today are going to be doing synchronous I/O. However, they almost always have an asynchronous counterpart. What's been around for a very, very long time in the Python world, in the early days of Python 2 even, is Twisted, which is a framework if you want to do asynchronous networking servers or clients. It supports basically every protocol that has ever existed on the planet. If you're more interested in web, there's Tornado, which is a asynchronous network library that is mostly a web server. And now, these days, since Python 3.4 or 5, we have async I/O in the standard lib. And built on top of async I/O, we have Scenic, which is basically the Flask of async I/O. It's incredibly fast, and I think later today we will have a talk about Scenic in particular. But there's also Curio, which is an interesting thing because it does asynchronous networking, but it doesn't use async I/O. It's a completely different implementation. And basically, what I'm trying to show you here is that when I talk about async, I'm not specifically talking about async I/O. I'm talking about asynchronous networking, which can be done with async I/O. It can be done with Tornado, with Twisted, with Curio, et cetera, et cetera. And for popular client libraries that exist in the synchronous world for a long time in Python, there's usually a very good asynchronous implementation these days. So there's AIOPG, which is an insanely fast Postgres client for Python. And according to their own benchmarks, they're faster than the Go client to talk to Postgres. There's AIO Bodo Core, which we use heavily because we use AWS Web Services a lot. And since it's me that's giving the talk, I will just shamelessly plug some libraries I wrote. In particular, Scenic, which is a web browser automation tool. If you've used Selenium ever, this is Selenium for async. And AAPNS, which is an asynchronous client library to talk to Apple push notification services. If you want to send push notifications to iOS devices from an async server, this is something that might be useful. And so before we can really dive into why you should go async, we have to understand a few core concepts of async I/O. In most implementation of asynchronous networking on Python, you have something called an event loop. The event loop is the main thing that will drive your application. And it's basically, as the name says, it's a loop that just waits for events and dispatches these events to different things. And the event loop is responsible for running so-called coroutines. Before we had coroutines, the most accepted way to do asynchronous networking was by using callback hell, which means passing callbacks into callbacks into callbacks into callbacks. If you've done JavaScript before the most recent few versions, you will know what I'm talking about, and you will know that it's not fun. And a coroutine, on the other hand, is a function. It looks like a function, it behaves most like a function, and it's a function that can cooperatively multitask. And it's important, the cooperative bit here is important because it has to actively want to do async stuff. It cannot just magically do the things for you. And another important thing is to know that when I talk about asynchronous, only the I/O is asynchronous. If you're doing logic, if you're doing CPU heavy, if you're doing computations, if you do something on the CPU, that is most likely still blocking. In other words, if you do a database query, that's going to be asynchronous. If you then do an if query, an if statement to check if the database query returned what you expected, that's going to be blocking. So back to my talk title, why you might want to go async. And I'm not going to hold back too long now and just say the answer is simple. The answer is money. Going async can save you a lot of money. So maybe a better talk title and why you might want to go async is, why does going async save you money? Now, a criticism that is often leveled against Python is that Python is slow. And if you compare it to something like C, that is pretty much just simply true. If you compare it to other things that are on a similar level of abstraction as Python, things get a little bit more hairy. And one big problem is if you compare, let's say, a Python web server, a Django server, against something like Golang, the Django server will always lose. And one big reason why it will always lose is by default, a Python server or client can only ever handle one request at a time, which is fine if you only ever have one request. As soon as you have two requests at the same time or very shortly after each other, things get very, very, very slow. And usually how we've done scaling, how you do scaling in synchronous world. So I used to be a Django programmer, and the solution is simple. Is you spawn more processes or more threads or throw more servers at it. But this is costly because every time you spawn another thread, another process, you need another C Python interpreter which has its own overhead in RAM, and you can only really run as many processes as you have cores, otherwise you run into the same problem as before. And the main problem with this kind of scalability is that we're still wasting a lot of CPU resources, because each one of these processes can still only handle one request at a time, which means every time it's waiting for something else to happen, like your database to respond to your query, it will just sit there and do nothing and literally waste your CPU cycles. And again, in the Django world, a common wisdom when optimizing performance was get rid of your database queries, optimize the hell out of your database queries, make sure your database queries, et cetera, et cetera, et cetera. Why? Because if you really looked at how your application was behaving, how your application was performing, most of the time it was actually not doing anything, it was just waiting. Sometimes people complained in Django that the Django template library is too slow compared to Jinja, which is true. Jinja is a lot faster. But in most real-life applications, this really doesn't matter because your template rendering is maybe 1% of your request handling time, which means if you make it twice as fast, your request is still as slow as before. So yeah, surprisingly little time is actually spent in Python code in most applications. And so making sure that we efficiently use CPUs is an important thing. So people say Python is slow. I say that is true sometimes, but it's not always true. I would say Python is mostly used inefficiently. Or Python is inefficient. And again, that's probably not true, because what I want to say is synchronous Python is inefficient. So let's use asynchronous Python and make everybody's life happier. And yeah, so I've been talking quite a bit here and giving you all kinds of abstract ideas and examples, but let's try a simple example. We will implement a web server that handles post requests. It will get the data from the post request, send it to a database. The database will return some sort of identifier, and we will return that to the client as JSON. So let's build it in synchronous Python in a made-up web framework. And our code might look a little bit like this. So you have a handler. Handler takes a request object, returns a response object. It will first read the post data from the request object, send it to the database. The database will return a primary key, and we write a response. Fairly simple stuff, I hope. And now let's look at what happens if we have two requests that come at the same time. And they will be indicated in the comments on the right-hand side. So you have two requests. You have a first request and a second request. So first request, we read the post data. First request, we send it to the database. We wait. OK, database returns. And we are ready to send the response back. Meanwhile, the second request was still waiting to ever have anything happen to it at all. So when the first request is done, the second request can finally be started, and it will walk through the same routine and finally be done. So the second request had to wait the whole time that the first request was processed, and the whole time itself, its own request was processed before it got a response. So let's fix this and make it async. And suddenly our request handler might look like this. It's still a function, and it still takes a request object. In this example, it doesn't return anything, which is kind of interesting. And it also has this weird new keyword in front of the function definition, async. Async def is how you mark a function as a coroutine function. An important thing to know here is simply putting async in front of your function does not make your function asynchronous. You have to still do something else. Async def just means this function can be asynchronous, not it is. The actual thing that makes it asynchronous is the await statement you will see in the 2 lines below. And that's the interesting thing here, is that we await on get post data and we await on database save. Why? Get post data is an I/O bound operation. You have to read the data from the client. If the client just sends you a small form, that's going to be not taking that long. But if he's uploading a video to YouTube, that's going to take a long time. So we await until this upload is done, and when this upload is done, we take the data and use it. And in this case, the way we use it is we save it to a database, which again is I/O bound. We have to write to the database socket data, the query, and then wait for the response. And in this case, we don't actually return a response, because in asynchronous networking, oftentimes returning stuff is not really that useful, because you will be returning data over time. So instead, we just create a response object, write data to it, and then say this response is finished. And yeah, the important thing is the biggest changes we've done is we changed the function definition to async def. We await I/O in both when we read it from the client and as well as we send it to the database. And we create a response object instead of returning a response object. Different frameworks will use different semantics for how they deal with this, but in this example, that's how it works. So let's look at our 2 requests again that come in at the same time. You have first and second, they're waiting to be handled. First request gets to the get post data stage, and the second request gets to the get post data stage. Why? Because while we're waiting for the first request to send all its post data to our server, we can also tell the second request, hey, we're ready to receive your data, please start sending your data. And in this example now, the first request was maybe on 3G, so it was uploading really slowly, while the second request was on really fast cable internet, so the second request actually finishes before the first with the uploading data. And then they will kind of walk in lockstep through, and every time there's an await, they can both run if they're both there at the same time, and they will both finish faster. Or rather, the second one will finish a lot faster, the first one will finish around the same time. And yeah, why does this work? In this example, we still used only one process, we only use one thread, we don't do any threading or anything like that. But while we wait for one request to send data, or we wait for that data to be sent somewhere else, we handle other requests. So yeah, that was a bunch of code, and I don't know if it was big enough to read or if it was easy to understand. So an analogy I came up with is you have a restaurant. You open a restaurant. So you buy a restaurant, you have a nice restaurant, you put one table in it, you hire a waiter, you hire a chef, and then your first customer arrives, and you're like, yes, I can make money now. So the waiter gets the customer and moves them to the table, takes their order, and now a second customer appears and at the door, and your waiter just ignores that customer. The waiter goes to the kitchen, tells them what food the first customer ordered. The second customer is like, hey, waiter, can I get seated? The waiter says, no, wait. Then, yeah, brings the food to the first customer, waits until the first customer finished eating, waits until the first customer paid his bill, and the first customer left the restaurant, and then the second customer can finally be seated and order his food. You're probably not going to make a lot of money if you run a restaurant like that, right? So how we would scale that in a synchronous environment is very easy. We just build more restaurants. So instead of having one restaurant, we build 10 restaurants next to each other. In each restaurant, we will have one table and one waiter, which means you have to pay 10 waiters. And when a customer comes, we just send the customer to the nearest open restaurant that doesn't have a customer yet. The problem with that is it costs a lot of money because you have to buy 10 restaurants, you have to buy pay 10 waiters a salary each month. So it's probably not ideal. And if you go to any restaurant in the real world, that's usually not how it's done. Instead, the restaurant will have more than one table, and maybe only one waiter, maybe two waiters, doesn't really matter. And when the customers come, the customers queue up at the door, and if the waiter has time, they seat them. And if a customer is ready to order, they raise their hand or they shout, and the waiter will eventually come to them, get their order. And similarly, the kitchen, when they're done with their food, they will ring a bell or shout to the waiter, and the waiter will deliver the food. Meaning, the customers are served asynchronously. If the first customer takes a long time to decide what food they want, but the second customer just wants a coffee, the second customer could be done before the first customer. Because the only time they block is when they have to talk to the waiter. So yeah, I hope that kind of made sense. So yeah, quick story time. At HDE, my company, my main project I work on is a Tornado web application. And Tornado is a little bit special in the async world that it allows you to both write synchronous and asynchronous server code. And so about half a year ago, I just got really fed up with how inefficient this thing was, and I just converted our most used APIs from synchronous code to asynchronous code. At that point, I relied heavily on threading because that's just easier to convert. You can, if you're using Tornado or asynchronous IO or async IO, you can say run this blocking function in a thread. And we still use the Tornado event loop, and at that point we still used Python 2.7. And the result was that the thing got 25% more efficient, meaning we could turn off 25% of our servers. And 25%, depending on how big your company is, might not be a lot. In our case, it was several $1,000s a month, US dollars a month that we could save by doing this. And the crucial bit is that our business logic, the thing that we actually care about, stayed exactly the same. Because the business logic doesn't really care too much about how I/O happens. It more cares about how, in our case, it's an authentication server, an access control server. So we care about who are those users allowed to access this resource, etc. And so this stayed mostly the same. And all I did at this stage was moving I/O code to non-blocking I/O threads. And yeah. So since hopefully it makes sense to you now why you should use async I/O, maybe a better question is why you should go async I/O now. Because we've had Twisted for a long time, we've had Tornado for a long time, we had other tools to build asynchronous code. So why do you want to do it now? And the biggest point here is Python 3.6. A quick show of hands for those of you who do use Python. Who uses Python 3? Okay, who uses Python 2? Wonderful. Okay, but yeah, Python 3.6. It introduced first-party support for async and await keywords. It supports async iterators and async generators and async context managers, which are amazing. If you're familiar with iterators and generators and context managers in normal Python, you probably know why they're so good. And yeah, they finally arrived in Python 3.6 supporting async statements. And this whole, and async I/O obviously landed in the standard library. And what this triggered is what I like to call the async revolution. Because again, nothing is really new about this. Async networking has been done forever. But in the Python world, it was always a little bit belittled. It was seen as this weird, twisted stuff, and the rest, all the cool kids use Django, and some people use Twisted, and that's not a nice thing to think, and it ignores the very valuable resources that we have. And thanks to async finally having first-party support in Python itself, it spawned all these cool projects which we can now use, which make our lives a lot better. There's UV Loop, which is a async I/O compatible event loop, which is built on the same underlying system as Node.js event loop is, and it's supposedly incredibly fast. Unfortunately, I've not had a chance to use it yet. There's AIOPG, which is probably the best Postgres client for Python out there. There's Scenic, if you want Flask, but you want to go fast. And then there's a ton of AIO prefix libraries for basically any database, any backend system that you could think of. It's most likely already been done. So let's continue our short story, my short story from before, where I just converted all our code in my company to something else. A few months ago, I got really fed up with Python 2. I was a Python 3 fan for a long time, but I got really fed up with Python 2, and I thought it's silly that we continue doing this. So basically, for a week, I secretly worked on a project where I converted all our code to Python 3.6. And in doing so, I found out that a very easy benefit thing I can do is change the Tornado event loop to be the async I/O event loop, which means I can use all those async I/O libraries that everybody's writing right now. Thanks to the upgrade to Python 3.6, I could remove about 20 dependencies, which were no longer needed, because Python got better and you don't need them anymore. And I only had to rewrite 2 dependencies, which were either not on Python 3.6, for the APNS library, or in the case of the Google libraries, they are on Python 3.6, but upgrading the library so far ahead just made it easier to just re-implement the things I need myself instead of upgrading. And we started using some async I/O libraries to do some specific tasks. And the results were quite drastic. The requests across the board got 3 times faster. And the request time got a lot more even, so there's less spiky response times. And once again, we could reduce the amount of servers we needed to run our application by about 30%, which again is a lot of money saved. So yeah, to recap, you should use async I/O or async networking to save money. You should use it now because we have Python 3.6 and async is ready. And you really should be using Python 3.6 or in the very near future, Python 3.7. If we have time and you have any questions, I will be happy to answer them. And thank you very much for listening.
Is anyone have a question? Okay. Yeah, this one. Why? Okay.
Hello. So I have one question. You talk about changing all of the code synchronous code calls into async calls when you still use Tornado. And then you converted that into async IO. But is it possible to use async IO in code that has synchronous codes in it?
So I maybe explained it wrong. We used Tornado before, we still use Tornado, but in Tornado you can choose which event loop you will use, and we chose the async IO event loop instead of the one by Tornado. And I changed all the code, and we still had some code which was blocking, which we could not convert or couldn't convert yet, because we want to do it over time. And generally how you do that is async IO has a function run in executor, which either runs it in a thread pool or in a multiprocess pool, whichever makes more sense for your thing. So usually what you would do is the stuff that you cannot upgrade yet or cannot upgrade at all, you would run it in a thread or a process depending on what exactly that code does. One of the others will be more appropriate. But yeah, you should try to not do that for IO. So whenever you have IO, you should try to use actual native async stuff. Otherwise, yeah, threads or a different process it's still the same thing as you would do in normal Python. Anyone else? Test.
I just want to ask about one of the things that hard on asynchronous from my point understanding is keeping consistency of data. How about as you said, like using IOPG for Postgres? How about managing the consistency of data written to the database and forth because the asynchronous processes?
Sorry,
yeah.
How to do what?
Like how to manage the consistency of data on that database because the data is written asynchronously.
I mean, that's how to make sure the data is consistent.
Yeah.
The same rules apply as if you were running synchronous code. If you run synchronous code, if you run it in production, you're going to run more than one process, right? Yeah. So two processes could talk to the database to the same record at the same time. So basically the consistency is a problem that your database has to solve, which in case of Postgres, it solves. Otherwise, you have to find a solution. But async doesn't actually, it doesn't affect consistency in my experience because it's the same as if you had to process. It's from the data point of view, it's the same as if you run two processes.
Okay.
Yeah.
So from like code standpoints, we don't have to do any changes or change the approach if you use asynchronous approach.
Yeah. So yeah, one thing, if you use, for example, threading, right? A thing you have to think about is locking so you don't mutate data at the same time. And because you use a single thread in async IO, that's not a problem. So it actually, in my experience, these kind of problems are easier to solve using async than other solutions to do concurrency.
Okay, probably we don't have time now. So we are thanks Jonas to share the information. Okay.